Alright, so now we are going to discuss forced response. Now forced response means, so previously we dealt with the differential equations where they are homogeneous. That means you didn't have a driving force. Now how about if you have a driving force? Well, let's look at an example and see what we can observe. But really forced response means when you have a driving force exist in the system. That means what is the differential equation going to look like? It is a non-homogeneous differential equation, right? Okay. Alright, so let's understand this from an example. So we have a spring mass system with a mass of m is equal to 1 gram and the spring constant k is 10 gram per second square. So we can find actually w square k over m, which is 10, right? Okay. And then the damping proportionality constant is beta is 2 gram per second. So if you divide by mass, 2 lambda is going to be 2 over mass is 1. So 2 lambda is 2. Okay. So we can formulate the differential equation. Now t square x dt square 2 lambda is 2 dx over dt plus 10x is equal to, now it is not 0 because it says a constant form of 20 dynes, so 20 here acts on the system. So that's the non-homogeneity, that's the driving force. Okay, and the initial conditions are the mass is pushed upward 1 centimeters. So the initial displacement is -1 because it's pushed upwards, and the initial speed is and release. So it's just the mass is pushed upwards and then it's released. So the initial speed is actually 0. Okay, so how do we solve this differential equation now? This is another application of chapter 4. What is the method you use to solve an unhomogeneous differential equation? Well, method of undetermined coefficients is the most suitable one. Okay, because we have constant coefficients here. Great. So you don't have to use like a method like variation of parameters. Okay, so how do you do is you first solve the homogeneous version, right? Find the complementary function. So the auxiliary equation is m square plus 2m plus 10 is equal to 0. Okay, so now if you use the quadratic formula to find the roots, -2 plus or minus 2 square is 4 minus 4 times a is 1, c is 10, so 4 times 10 is 40 over 2. So this is -2 plus or minus 4 minus 40 is -36 over 2. So the roots are, I will write them down fast but try to do it by yourself, -1 plus or minus 3i. Okay, so those are the roots. Try to derive it by yourself. So alpha is -1, beta is 3. So complex roots. Then what we have is complement, not y sub c, x sub c now. Okay, x is the dependent variable. E to the -t, e to the alpha t, c1 cosine 3t plus c2 sine 3t. So this is the complementary function. Okay, all right, now let's take into account that this is a non-homogeneous differential equation. So if you are using method of undetermined coefficients for x sub b, particular solution, come up with a guess. Now the non-homogeneity is 20. What type of a function is that? That's a constant. So your particular solution should be a constant, the initial guess. Now do we have overlap? Well, we do not have an overlap, right? So our guess is correct. So let's substitute our guess to the differential equation. So to substitute, we have to find x prime. Derivative of constant is 0. Second derivative is again 0. So it's much easier, right? So if you substitute it into the non-homogeneous differential equation, 0 plus 10 times a is equal to 20. So this means a is 2, right? So the particular solution is actually 2. This is a very easy example, by the way. Okay, so we can write the general solution as the summation of complementary solution e to the -t c1 cosine 3t plus c2 sine 3t plus the particular solution plus 2. Okay, now what we have to do is we have to use the initial conditions. So when t is equal to 0, x is -1. So -1, when t is equal to 0, this term is 1. C1, cosine 0 is 1, sine 0 is 0. So it's C1 plus 2 here. Okay, so C1 is going to be like -3. Okay, so now to find C2, we have to use the second condition. So we have to find the second derivative. So second derivative of this function is you have to apply the product rule to the first part. So it will be like first let's apply product rule term by term. Let's write it as C1 e to the -t cosine 3t, distribute e to the -t, plus C2 e to the -t sine 3t plus 2. So if you apply product rule here, negative C1 e to the -t cosine 3t. Now you differentiate cosine, which you get -3 C1 e to the -t sine 3t. Here if you apply the product rule, negative C2 e to the -t sine 3t plus 3C2 e to the -t cosine 3t. If you differentiate 2, that's good. Now if you substitute 0 for t, x prime is actually 0. So when t is equal to 0, here negative C1 cosine 0 is 1, sine 0 is 0, sine 0 is 0, plus cosine 0 is 1, e to the 0 is 1, so plus 3C2. Okay, so C1 is -3, so this becomes 3. So when you take it to the left, -3 is 3C2, C2 is -1. Okay, right, we are done at last. So the solution, not the general solution, the solution is e to the -t, C1 is -1, so negative cosine 3t, C2, oh, C1 is actually, I think, something else. C1 is -3. So here it should be -3. So -3, negative e to the -t sine 3t plus the particular solution 2. So this is the solution of the differential equation. Okay, now let's discuss. Now what do you think happens eventually? We didn't discuss that. Is it the same as damped motion with a homogeneous system? No. Now think what happens in this system. When t goes to infinity, so limit when t goes to infinity of the x, okay, these are exponential functions, right? So they approach to 0. Comparing to this cosine and sine, exponential dominates. So those two approach to 0. So do we actually approach to equilibrium rest position? No, because don't forget you have 2. So actually the displacement will be 2. So the motion will not approach to the rest position. It will approach to the a displacement of 2 from the initial rest position. So that's the biggest change from a homogeneous differential equation you saw before. Okay, so the motion is going to anyway stop here. Okay, in this particular thing, the motion is going to stop at a displacement of 2. So if you look at graphically is also, it makes sense. So if you look at the graph, here is the graph, as you can see. So you have some oscillated motion because you have sine and cosine terms in the solution, remember, but you gradually approach to x is equal to 2, like, okay. So really, what is x is equal to 2 means in this problem? What is 2? 2 is, if you haven't forgotten, that's the particular solution. Okay, so what really happened is eventually the system behaved like the particular solution, or the system is, I would like to say, completely driven by the driving force effect, because we get a particular solution because of that driving force, right? Because of that non-homogeneity. So that is what decides the eventual behavior of a non-homogeneous system in a spring mass system. Okay, in a non-homogeneous differential equation. So remember, particular solution is the behavior, eventual behavior of this type of a system. We will see another interesting, beautiful example in the next question. Okay, all right, so that is another skill you should have. You should be able to read the solution and you should be able to understand the whole scenario. Okay, all right, thank you.